record this meeting. Yeah. Hi, Connor.
Hey, Mr. Cohen, how's it going?
Good. How's the calculus going?
Well, I feel pretty good about the intro to calculus and maybe calculating some limits now.
Okay.
We have gone over in class infinite limits, limits at infinity,
Okay.
and kind of getting into continuity now.
All right.
So I wanted to, if you don't mind, go back a bit here and talk about transcendental functions.
That is fine. Whatever you want to do, that is fine.
Okay, so let me give you a problem here.
Okay.
This is
Transcendental functions. I have not heard that term in a while from a student.
okay. Well, good. Maybe not good. We'll see. This is f of x is equal to cosine of x, and x equals pi over 2. So the question here is asking to define the slope and then use the slope to determine the tangent line equation.
Okay. So, how do we find the slope?
With the rate of change.
We take the derivative. That's the same as slope.
Okay.
Whenever they want you to find slope, you need to think derivative.
We haven't learned derivatives until chapter 3.
Ah, okay.
So that's why I'm asking. I know you're excited to get to the derivatives part.
Yeah. Okay, well let's draw this curve. And pi over 2 is right there. And that is y equal cosine x. And I haven't quite drawn it accurately enough. Let me draw it again. More like that. So if you look at when x equals pi over 2, what's the slope of that curve of the tangent line? Right there.
Is it, I mean, if it's a straight line, it would be 0. Is that fair to say?
No, only horizontal lines have a slope of 0. That straight line happens to have a slope of -1.
-1, okay.
And here's, I don't know how to explain it to you other than by derivatives. But if I want to know the slope of that, then, I mean, you're going to get to this eventually, so this isn't going to hurt. Might not help at the moment, but you have to memorize the first derivatives of trig functions. And the first derivative of cosine is minus sine. Okay? Now, maybe we could figure that out by the quotient formula? We could actually, but for the moment, let's just accept that that is something you're going to memorize. And now, what if you say, what is the slope at pi over 2? Then I'm going to plug it into this, minus sine of pi over 2. Well, sine of pi over 2 is 1, so that's minus 1. And that is the slope of that tangent line.
Okay.
Now, we didn't come up with an equation of that tangent line, and that is frequently the task, is to come up with the equation of this line. Well, we can do that. Let's draw it in blue, first of all. And the reason we can come up with the equation of it is because we have a point and we have a slope. So, are you familiar with the point slope formula?
Yes. Y minus y naught equals m paren x minus x naught.
Mm-hmm.
Close paren.
Well, we just figured out what... I figured out what the slope was by taking the derivative of it. So for the moment, the only point we know for sure that's on that line is this one right here, correct?
Correct.
So what's y naught?
Would be 0.
And slope, because we figured out the derivative. And x is what? What's x naught?
X naught is 1.
It's pi over 2.
Pi over 2.
This
Okay,
is
sorry.
the x-axis. So we're at pi over 2. And that equation of that line turns out to be pi over 2 minus x. Or minus x plus pi over 2. So there's the equation of the line.
Okay.
Now, in order to get that, I had to know the slope and one point. And you get the slope by taking the derivative. Now, let's see if we could take the derivative of this using the derivative definition. In other words, first derivative is equal to the limits of f of x plus h. I'm presuming this is the way they want you to do it?
The way that we've gone over it in class is f of x minus f of a over x minus a.
Ah, okay.
So it's not quite the quotient
at a certain point.
Yeah.
Yeah. That's a perfectly fine way to figure it at a point. It's not nearly as robust as figuring the derivative of the function itself.
Mm-hmm.
And then substituting that point. That covers all bases, whereas the derivative or the slope at a point only covers the slope at that point.
Okay.
So I tend not to ever use that because I know how to take the remember that derivatives are manipulations of functions. So let's see what happens if we try to figure this out without. So if f of x is cosine x, what is f of x plus h? Because that's where you always need to begin, right there.
Okay. So we have cosine of x minus plus h.
And then, of course, we have the f of x. So we can go straight into cosine. I'm not going to ignore your problem. We can look at that after we do it this way. I want you to realize, though, that this way is the better way. In other words, where you actually figure out the derivative of the function rather than the slope at a point. And we can do it both ways. So I want the limit of this as h goes to 0. This is using the definition of first derivative. This is the official definition of first derivative, the ultimate math definition.
Okay.
And how do you solve this? By using trig identities. In other words, it's not the easiest algebra, but if you use, remember the sum and difference formula?
Ah, okay.
So that is cosine of x plus, excuse me, cosine.
Yeah, hang on. It's sine of, well, I guess it depends which one we're doing. We're doing cosine.
We're
right?
doing cosine. So
cosine of A times cosine of B plus or minus sine of A and sine of B.
whoops. This Zoom is not perfect. It kind of gets in the way sometimes. Minus, it's actually plus.
Okay.
Because that's a minus. No, excuse me. Because that's a plus, it's a minus. In other words, it's opposite.
Right.
When you're doing the sum and difference, it's opposite. So it's this. And if you go through that math, you get minus sine of x. Now, that's not intuitively obvious.
But this should get you the same thing as the derivative, is what you're saying.
Yeah, in other words, this is the way all derivatives were originally calculated. You know, and then somebody discovered, well, wow, you know, the power rule works on a polynomial, and you can just memorize the trig functions, and the first derivative of cosine is minus sine. The first derivative of sine is plus cosine. So, solving this right off the top, I'm not sure how we're going to do that. I can't think of how we would do that at the moment. And regardless, that is beyond the scope of where you're at right now.
Right, yeah.
So there's no way they want you to do it that way. So let's go back and maybe do it the way they want you to do it. Where the derivative at a point instead of the derivative of the function is equal to the limit of f of, what is it? I use it so seldom.
So it's f of x minus f of a over x minus a.
As x approaches a. Correct? Or as a approaches x, maybe?
Well, that would be right. I mean, it's, I guess for here in this problem, that's the basic formula for this.
Right. That
Right.
that is the definition of the slope at a point A.
Right. Right.
And that will give you the answer, I guess. We'll have to work through it. Um, the only point I want to make is that once you go through this exercise where you figure out the derivative at a point, and then you discover that if you take the derivative of the entire function, that covers all points, then you never really do it this way again. There is one time where this is needed, and that's when you're trying to prove continuity. So that is probably the reason you're getting it at this point.
Because the way, so I tried this, there's a couple of these, you know, transcendental problems, and I tried for a couple hours to solve them. But what I think it ends up needing to be is because of this, because of where we're at in terms of introduction to calc, it ends up being that you take points. The teacher describes this as solving the problems numerically. So you would take points around that, you know, pi over 2 to approximate what the slope would be. And
Okay.
then you would use that
Okay. And then you can
approximation
see what it's converging to.
Yes.
Yeah,
Yes.
exactly. Yeah, I'm not,
Well, I'll tell you what, I don't want to spend too much time on it because these are problems for participation. And I think I was just
hold on.
curious of seeing
Before
another
we
way.
leave this, let me just see what happens here. A is pi over 2. So
Right.
cosine of pi over 2 is 0. And then it's x minus pi over 2, x minus a. And we're looking as somehow this comes out to be minus 1. You know, it's been so long since I've done it this way because it's the non-robust way that I kind of forget how to do it. I can open my book and find this particular definition, but that particular definition is only used when you really are trying to disprove continuity. Because you can prove that the slope from the left is not, in other words, if you have a function like this, not so much discontinuity. What's the slope right there? What do you think it is?
I'm guessing 1.
Undefined.
Okay.
You cannot take the derivative at a corner or a cusp. Okay? And the way you prove that that's undefined is by using this point. In other words, there's the point, say whatever, pi over 2, and you find out that the slope from the left is not the same as the slope from the right, therefore you can't take the derivative at that point. One might estimate that the derivative looks like that, but that would be wrong. You cannot take the derivative at corners or cusps. If you have a function that looks like this.
Then you could.
Nope. Cannot take the derivative right.
Oh, okay. I thought you were going to.
That's a cusp.
I
That's
apologize.
a cusp. In other words, if you have a point between a curved line and a straight line, that's a cusp. This is a corner. The derivatives do not exist at those points. And it turns out that the way you prove that is by this particular derivative at a point formula.
Okay.
And it sounds kind of like that's where you're at. is they want you to do that.
Yeah, she explained to me that all these, at least at this level for where the class is at, where I'm at with calculus, is that the transcendental functions will basically be, you know, approximations or solved numerically, not the same way that polynomials are. So I guess I guess I was just curious to see. I don't want to. I've got some other questions I wanted to ask, so I don't want to. I don't want to
Okay,
spend too
yeah, we
much
don't
time
want
on it.
to take up all of our time with this esoteric point.
Yeah, this
It
we
is an esoteric point. It
we
is
can revisit
not.
this because I will be seeing you a couple times this through Sunday or so or next week because I have my first test.
Okay.
So I want to study up on everything for sure. But um, obviously I want to get through some of the subject matter as well. So that's okay.
Yeah, hold on 1 second. Let's see if I can maybe clear this up quickly. Hmm, hold on. Yeah, it's this definition here. Okay. Let me erase everything I've written here. And the other definition of first derivative at a point is f prime of c, that being the point, is equal to the limit of f of x minus f of c all over x minus c as x approaches c, interesting, from the left. Huh. I've never noticed that before, but that my calculus book has that in it. And
Okay.
so you could solve this problem about cosine using this definition. And I don't know, I could, in fact, I wouldn't doubt that they have a trig function as the, no, they don't. Might be kind of tough to do with a trig function. So, well, hold on. Let's just see what happens here. So, f of x is cosine of x. F of c is 0. And we have x minus pi over 2. And we want the limit of that as x goes to pi over 2. It's not clear at all how that turns into minus sine x.
I'm just guessing here because I do well. I'll say this: in sections 2.1, 2.2, where you're introducing the concept of a limit and things of that nature. A lot of what we were doing to arrive at a slope was doing this formula as we get closer to the point of C. So you're kind of approximating it when you
Yep.
get to instantaneous
Yep.
value.
I get it.
I'm assuming it's similar here, whereby we'd be taking another couple of points around pi over 2 to
Yes.
kind of
Do you have a text? Do you have a textbook?
I don't have a textbook. I have notes.
Okay.
The teacher,
Because when you're saying chapter 2, my textbook, this is exactly in chapter 2. So I thought maybe we had the same textbook.
well, it's possible actually. Now that I think about it,
Mine is Calculus of a Single Variable by Larson, Hostetler, and Edwards. It's the textbook of choice for Colorado for calculus. So even if you don't have this textbook, in all likelihood your teacher is using this textbook to teach you calculus.
who was the author again?
Hostetler, Larson, and Edwards. The main thing is calculus of a single variable.
Huh.
Because there is calculus, higher level calculus, where you have two variables or multiple variables. Most all high school calculus is calculus of a single variable. It's not really until you get into college and higher levels of calculus that you get introduced to multiple variables.
Okay.
But let's not get bogged down here.
I was gonna say let's switch gears. I'm gonna move into
However, before we go further, I want to give you this because it's never too soon to memorize what you're going to need to know. You need to memorize all these derivatives. And there is a pattern here. The derivative of sine is cosine. It's cofunction. The derivative of tangent is secant squared. The derivative of secant is secant tangent. And those are the first three you want to memorize. And that's not the way they're taught. They teach you the sine and then the cosine. But this is a better way to memorize it. These are your three non-cofunctions, correct? They don't start with a co. They start with sine, tangent, and secant.
Okay.
So memorize that the derivative of sine is cosine, the derivative of tangent is secant squared, and the derivative of secant is secant times tangent. And then the other three are all minuses with the cofunction. So what's the cofunction of cosine? Sine. What's the cofunction of secant squared? Cosecant squared. And what are the cofunctions of secant and tangent? They are cosecant, cotangent.
Okay.
So this is another case where you have to memorize three things and you can figure out the other three things always. So the key ones are those three. If you can memorize those three, you will always know the other three. Because the other three always start with a negative sign and they're merely the cofunction of what the sine is.
Okay.
In this case, it's the cofunction of secant. In this case, it's what the cofunctions of secant times tangent are. So memorize the three that I have checkmarked, and memorize the method of finding the other three.
Okay, I took a picture of this, so.
Yeah, that's something you're going to need very soon. Maybe not until you get through this chapter on continuity and this question of the derivative at a point versus the derivative of a function. Pretty much once they teach you the derivative of a function, then you only use that. You never go back and figure out the derivative at a point. You just don't. Because the derivative of a function is so robust that once you take the derivative of a function, then you can figure out what the slope is at any point by just substituting it into the derivative.
Okay, noted.
So when you said what is the derivative of, or what's the slope at cosine of pi over 2, well, I know that that's the derivative of it. And if I substitute pi over 2, the sine of pi over 2 is 1, so that's minus 1. So I can instantly figure out the slope at any point on the x-axis merely by knowing the derivatives of the functions. And I don't really have to ever use this other method where it's f of x minus f of c all over x minus c. That is needed for one situation only, and that is to prove that you cannot take the derivative at a corner or a cusp.
Okay, noted.
And that's not that big of a thing. Yeah, so let me clear this and I'll let you give me some more problems that you want to look at.
Okay, so these are limits at infinity here. Okay, so
So the limit as x goes to infinity?
yes. And these are the same problem. It's just as the one's going to approach infinity and then the other one's going to approach negative infinity. So you probably don't need to rewrite it twice, but just as an FYI. So the square root of 10 plus 5x squared all over 4 plus 10x.
So if there was no square root in the numerator, what would the limit be? If it was just 10 plus 5x squared all over 4 plus 10x. Because the exponent is higher in the numerator than it is in the denominator,
Oh, it's a slant.
got to be infinity.
Okay.
In other words, if I take away the radical sign, the numerator is always going to grow faster than the denominator.
Okay. Okay.
Let's start with something a little bit easier, which is what is the limit of 5x over 3x as x goes to infinity. What's that?
So is that just 5/3 then?
Yeah, it's the ratio of the coefficients, which is what
Gotcha.
you learned about horizontal asymptotes. And that's exactly what a horizontal asymptote is. In other words, if I have a curve and I've got a horizontal asymptote here, right there, then what I'm saying is what is the limit of that function as x goes to infinity? And it approaches that horizontal asymptote. Always. Okay? So this problem would be easy because we know it's just because we have an x in the bottom, I make that x squared. Now what's the limit?
Is this, well, okay, hang on.
Infinity.
So this is to infinity.
Yeah, because what happens is that I can take, that's the same as this. And as x goes to infinity, this number goes to infinity.
Gotcha.
Okay? So the only time, oops, what was the bottom? 4 plus 2x?
4 plus 10x.
Plus 10x. Now, this is a little strange because if I said, what is this? What's the limit of that as x goes to infinity?
It would be 25.
Be 5.
5.
In
Okay,
other
sorry.
words, when you take the square root of that, you get 5x, right?
Right.
So you'd have 5x over x, so it would be going to 5. Now, they complicate the situation considerably by putting it into this format over here on the left, because you can't take the square root of 10 plus 5x squared. But you know that if you could, it would bring that down to x. In other words, that's going to be an x in the numerator, and I'm going to have an x in the denominator. So the way you really solve this problem is by ignoring the number, which is frequently the case when you're dealing with limits as x goes to infinity. And now I operate only on the variable part, and I get this over this.
Okay.
That's going to go to that limit. Now, it's been a while since I've done this kind of a problem, and I feel like I want to put this into Wolfram Alpha just to verify that I'm correct, but I don't need to think about it. Do you have answers on these?
I don't. The software is not as robust as the last
Here,
semester was.
let's put this into Wolfram Alpha just so I don't.
Because yeah, basically we would just need to know if it's heading towards infinity or heading towards negative infinity.
Yeah. Well, this one's headed towards a number.
Okay.
But Wolfram Alpha is pretty cool. It'll let you do most anything like calculus. In other words, I can put it in as a, and it'll give me the answer. But pretty sure that root 5 over 10 is the answer. Unfortunately, with Zoom, it hogs so much of your bandwidth that it's difficult for me to go use Wolfram Alpha or any other website to figure out these limits. That's why it actually would have been easier if you had answers, because then I wouldn't have to waste time going to Wolfram Alpha. And it clearly is looking like it. Oh, okay, here. Let's see what happens here. This is a good resource for you. So, what did we have? We had, what was the top?
Square root 10 plus 5x squared. And that's all over 4 plus.
Hold on, that's not the square root yet. I got to take that to the 1.
Oh, to the half power.
Yeah, to the 0.5. And then I'm going to divide that, the whole thing. So I probably need double parens. In other words, I'm dividing that entire numerator by what?
4 plus 10x.
Okay. And let's see what happens. It probably will stick in infinity in there on its own. No, it doesn't. Yeah, here you go, right here. See where my cursor is?
Yeah. So 1 over 2 square root of 5.
And I'll bet you that's the same as what we got. In other words, is that equal? What did I come up with? Square root of 5 over 10? Notice that mine is rationalized and theirs is not. But if I multiply my answer by square root of 5 over square root of 5, we get 5 over 10 square root of 5, and then that becomes 1, and that becomes 2. So we did get the right answer. And the key on these problems is to ignore the constant. The constant rarely has anything to do. If I said, what is the limit of x cubed plus a million, the million doesn't have anything to do with it as x goes to infinity. That could be a billion. And as x goes to infinity, this whole thing goes to infinity. As x goes to negative infinity, the whole thing goes to negative infinity. In other words, if I wanted the answer to that, you just ignore the constant. Because the variable always overrules the constant, always overtakes it, always matters the most. So when I see this problem here, what I'm really doing is taking that, the square root of 5 in the numerator over 10 in the denominator. That ends up being the ratio of those coefficients.
Right.
Because you know when you take the square root of x squared, you're going to get x. And so I'm going to have an x in the numerator and an x in the denominator, and as long as the powers are the same, whether it's, x squared over x squared or x over x, then the limit always goes to the ratio of the coefficients. And in this case, the ratio of the coefficients, the top is the square root of 5. The bottom is just 10. So that's how I got the answer.
Gotcha. Okay.
And then oddly enough, they give it to you in an irrational denominator, which I find kind of interesting.
Let's see.
But anyway, so I am correct on how to do these, and I can at least minimize this. I don't think we'll need it anymore. What else you got? It is worth using Wolfram Alpha for yourself. I'm sure that there's going to be, like if you wanted to know what the answer to that was. You're saying your software doesn't give you answers, that'll give you the answer.
Okay. Yeah, I mean, it doesn't, it'll tell you if the answer is correct. It just doesn't tell you how to get to.
Okay. So if you get it wrong,
like if you enter it wrong,
what the correct answer is, yeah.
Okay, so here's another.
Okay, go ahead.
So the inverse tangent of x squared minus 4, minus x to the 4th power as the limit approaches infinity, as x approaches infinity.
Okay, when you're talking limits as x approaches infinity, the only term that matters is the largest polynomial term.
Okay.
In other words, if I had a function x to the 5th plus x to the 3rd plus x squared plus 100x, and I wanted to know what this limit is as x goes to infinity, this is the only term that matters. None of the others do. Because it always overrules. Always. So when you're talking limits of a polynomial, you're really talking only the limit of the first term. And in this case, this is what's going to rule. And Wow. So we're going to end up taking the limit, the inverse tangent of minus x to the fourth. As x goes to infinity. Now, let's look at the tangent line.
Okay.
The tangent curve. Now we'll talk about the inverse tangent curve. This is the tangent curve. And it goes from minus pi over 2 to pi over 2. And so, if they were talking about tangent, then as x goes, because this thing just repeats forever, okay? So the tangent of infinity is undefined.
Okay.
But the inverse tangent of infinity, in other words,
Just horizontally.
yeah, exactly. The inverse tangent is the inverse of the tangent. And so you talk about when we go to positive infinity, we're going to there. And the inverse tangent is approaching pi over 2 as we go to positive infinity. Now, are we going to positive infinity or negative infinity?
We're going to positive infinity.
Actually, I think we might be going to negative infinity. Because if we're going to focus strictly on that, then this is the problem. We're taking the inverse tangent of minus x to the fourth. And as x goes to infinity, this quantity goes to negative infinity. So we're really looking at way down here. So we're probably approaching minus pi over 2. That's what I'm going to say the answer is. And we're going to use Wolfram alpha. Shouldn't take that long this time.
Okay. That's the correct answer. I just typed it in, so that worked.
Okay. The logic of how I got there was a little bizarre, but these problems are pretty difficult relative to limit problems.
I didn't even know how to start it. It made sense what you did. It made sense what you did. I just didn't actually.
Yeah, I'm trying to think if I could have done it in a better way. But no, actually, I think I did it in the correct way. In other words, you start by, oh God, I cleared everything out. But you start by eliminating your lower degree polynomials. And so you start off with minus x to the fourth. And if you look at the, this has always been difficult for me. I can draw the tangent curve really easily. Drawing the inverse tangent curve is a little harder. I guess it's going to look something like this. Yeah, where this would be minus pi over 2. In other words, when you look at inverses, the x and the y change. This becomes the x-axis. So this curve here would be the inverse tangent curve. And if I merely look at that curve and project what happens as x goes to minus infinity, we can see that there is an asymptote right there at minus pi over 2, so that as x goes to minus infinity, it's approaching minus pi over 2. Now, did I draw that curve properly? Well, let's find out. The way you draw an inverse curve is you draw the line y equal x, and then you reflect your curve about that. And so if I try to draw it in blue, it is going to look something exactly like I drew before. So the blue curve is the inverse tangent curve.
Okay.
And when you look at the problem like that, then it's really clear, and that's minus pi over 2, because the red curve goes from minus pi over 2 to plus pi over 2. So the inverse curve, the asymptotes are going to go from minus pi over 2 to plus pi over 2. You just reverse your x and y coordinates, basically.
Right.
And now it's easy to see that as long as you're taking the inverse tangents of minus 4x squared, not minus 4x, minus x to the fourth, right?
Right, right.
Well, as x goes to negative infinity, as x goes to positive infinity, then that actually goes to negative infinity. And so it's this part of the curve that I'm looking for where it is approaching, and it is approaching minus pi over 2.
Okay, I think I follow.
Okay.
Because if I guess, just to check my understanding, had that not been the inverse of tan, but still the negative x to the fourth, we would be going towards negative infinity, right?
Well, actually not.
Okay.
Because here's the problem. Let's just talk about the sine curve. What's the limit of the sine of x as x goes to infinity?
Isn't this not determinable or indeterminate?
Yeah, it isn't, because you can see that it constantly fluctuates.
Right, oscillate.
So as you go towards infinity, sometimes it's 1, sometimes it's 0, sometimes it's minus 1, sometimes it's any number in between. So it's an oscillating thing.
Right.
So that limit does not exist. And it's quite similar to the tangent curve, where it's going to be something like this, followed by this, followed by this. And so if you said, what is the limit of that function as x goes to infinity? Well, it's oscillating. The answer goes from minus infinity to plus infinity, depending on where you go. So you can't always find limits as x goes to infinity. Sometimes they just don't exist. And the tangent curve is such a thing. However, when you talk about the inverse tangent curve, that's totally different, because that looks like this. And it actually has these same asymptotes, only they're horizontal, and they're at minus pi over 2 and plus pi over 2. So now, if we talk about the inverse tangents, we can figure out what the inverse tangent had. If x goes to infinity, what's the inverse tangent go to?
Pi over 2.
And if x goes to minus infinity, what's the inverse tangent go to?
So then it'd be negative pi over 2. Okay.
Exactly.
Okay, that makes sense. Okay. All right.
It seems to me like they're making this overly hard. They're giving you really difficult problems, limit problems, and I guess that's fine. Eventually, you have to deal with them.
It's the infusion of everything, though. It wasn't, these weren't so bad when they were polynomials, but I just don't even know what to do. Like, for example,
Yeah,
if you don't mind this, if we can do one more, that'd be great.
sure. No,
This
for
is
sure.
So this is the cosine of -4 over x as the limit approaches positive infinity. So it's this introduction of bringing in these, these other type of functions, the trig and whatnot, that are really um, causing a blank for me here.
What happens to that as x goes to positive infinity? In other words, let's start by that. What's the limit of -4 over x as x goes to infinity?
The limit I guess would it be would it
If
be
the
infinite?
bottom if the bottom blows up and the top stays the same, it's
Gets
always zero,
Oh, okay,
right? In other
right.
words, make x 1,000, that number is small. Make it 1,000,000, that number is even smaller. Make it 1,000,000,000, it's even smaller. As it finally hits infinity, it's zero.
Okay.
Okay? So this is the same question as what is the cosine of zero?
Okay, so that's 1.
Huh? In other words, this is a straight substitution problem. You're going to substitute infinity for x, and then you're going to figure out what happens to the argument as when you substitute infinity for x. And the argument goes to 0. So you're
Ah,
really looking at the cosine of 0. And the cosine of 0 is 1. If this was sine, then the sine of 0 is 0.
gotcha. Okay.
Okay? So some of these can be done by straight substitution. The two problems you gave me prior to this are, I would say, on the high end of the degree of difficulty for this section, limits. Um, just because it is, they are. This one, not so much. This one is straight substitution, fairly straightforward. You don't have to make any assumptions, like when you have the radical in the numerator on that first one. You have to ignore the constant and work only with your variables. That's a trick on some of these limit problems. But this one's a straight substitution problem.
Okay. And that's, I guess, on that note, that's, I should always be thinking of that, though, right? I should always just try to
Always
eliminate
as a first
substitution.
step. Yeah,
Yeah.
yeah,
Okay.
yeah. But that usually doesn't take you very far because you immediately
Right.
realize that it doesn't lead to a direct answer. It either leads to 0 over 0. In that last problem, it actually did lead to a direct answer because you know what -4 over x goes to as x goes to infinity. It goes, if the denominator is blowing up and the numerator is staying the same, then it always goes to 0. If it's the other way around, where if I said what's the limit of x over 4 as x goes to infinity, well, now you have the numerator blowing up, the denominator stays the same, that's going to go to infinity. And that's a pretty good way to think about it, as which grows faster, the numerator or the denominator. And if one obviously always is going to grow faster, then you know what your answer is.
Gotcha. Okay. That makes sense. much going. That's probably a pretty good place to stop.
Okay.
I'm definitely going to be. I'm gonna see you at least for 2 more times. So I'm just trying to round out where my gaps are and then be able to focus on those. So I will contact you tomorrow and probably set something up for tomorrow as well.
Yeah, sounds good.
All right.
And let me just say one last thing. It's going to get easier from here forward for a while. For quite some time, it'll get easier.
Okay.
They're
That's good
they're
to know.
challenging you with difficult questions for the section that you're in, and not really anything that you actually have to pay attention to for the future. Because once you get past limits and you get into all these rules for differentiating functions, then it becomes a lot easier. Then it's just a question of memorizing the rules, substituting where appropriate, and it actually is a lot easier. So try not to get demoralized before you get to there.
Okay. No, that's good to know. I'm getting more comfortable with this. It's just that for most of this limit stuff, introducing then like logarithmic exponential problems and trig problems makes me just kind of freeze up. So
What is the most unique thing about that function? E to the x.
the most unique thing about it,
Huh? It's the only function in the world whose derivative is the same. If y is equal to e to the x, y prime is also equal to e to the x. And there's no other function that does that.
okay,
And that becomes significant because that's the next place you're going to go once you get beyond limits, is they are going to talk about exponentials and derivatives of exponentials.
okay,
And that is pretty special. The fact that e to the x's derivative is e to the x. Um, so anyway, I'm sure you'll get taught a lot of this.
yeah. Chapter 3 is the introduction to derivatives, so we'll see what
Yeah,
they bring us.
yeah.
But that's what the
But you'll
game for
find
me
that
is.
you're going to need to memorize your trig derivatives, you're going to need to memorize your inverse trig derivatives, and you're going to need to memorize your log or exponential derivatives, like e to the x. Memorizing that the derivative of that is e to the x.
Okay.
Um, but other than that, I really truly think it'll get quite a bit easier once you get beyond what they're trying to teach you now.
Yeah, and I think some of this too, this is unrelated, but some of this too is the way the teacher teaches is kind of disorganized. It's not as effective as the last teacher that I had
Yeah,
was. So
it's got to be hard.
it happens. It happens. I mean, not
Is this,
everyone.
are you doing in person?
No,
Entirely
this is
online?
yeah, this is asynchronous. It's just that like the last for Trig, the way the guy set it up was once a week you would learn a new concept, you would do the homework, and then at the end of that week you get tested on it. That would happen for a unit in which you got tested for the exam.
Yeah.
And he just had these videos you'd watch that was breaking down just each part of those concepts. So it was very straightforward and all of this. The software for the homework was a lot more robust too, where like if you didn't know how to do the problem, you could have it solve it for you and see what they do, and then you could do a new problem of that.
I tell you what's really valuable in calculus is knowing the answers. I mean, it might seem strange to say that, but frequently, if you cannot figure out how to do a problem and you know the answer, that leads you to be able to figure out how to do the problem.
Interesting.
And that's why most calculus books will have the answers to all of the questions at the end of each chapter. Whereas prior to calculus, when you were taking trig, they'd usually only give you the odd number answers. Or algebra, they give you the odd number answers. But with calculus, it's so important to know what the answer is because there just are too many times where you can start with the answer and go back and figure out how to do the problem, which is an important capability. So having the answers is pretty helpful.
Okay.
Not from the point most people would interpret that, but it's helpful in figuring out how to do the problem. Not just in getting the answer. Obviously, having the answers is great if you're taking a test, but in calculus, it frequently shows you how to do the problem if you know the answers.
Okay, that makes sense.
All right, Connor, I will talk to you later, and
All right.
have a
You have a good day. I'll talk to you soon.